in the homework assignment that I gave out after the quiz, you discovered, hopefully on your own, a couple of new formulas, geometry formulas using trigonometry, and I just want to review briefly what those are. So first of all, we derived, or you derived, a new formula for the area of a triangle. Now, while I'm at it, I want to emphasize that we kind of have a certain convention when it comes to labeling the angles and the sides of a triangle. In this class, we'll use capital letters to represent angles and lowercase for sides. Also, we'll adopt the convention where the side opposite of angle A will be side A, lowercase a because it's a side. And similarly, the side opposite angle B will be little b, and this side will be little c. Okay, now if we want to write down a formula for the area of this triangle, previously in other courses, you'd have to use the old area formula, which is k equals 1/2 base times height. For whatever reason, we tend to use k to represent area in this class. So this is the old area formula for a triangle, but you discovered a new area formula that says k is equal to 1/2, well, one version of it is AB sine capital C. That means the length of this side times the length of this side times the sine of the angle in between those two sides. This formula is really nice because it doesn't require that you know the height. Finding the height of a non-right triangle can be pretty tricky. Like you'd have to find the length of this perpendicular segment here. Not very easy to do in general. So this thing is great because you don't need the height. Of course, there's other versions, right? It's not just 1/2 AB sine C. You could also write it as 1/2 BC sine capital A, or finally 1/2 AC sine capital B. The big picture is the area is going to be given by 1/2 the product of two sides, and then times the sine of the angle in between those two sides. So whatever version of this formula you use, it doesn't make any difference. It's just 1/2 one side times another side times the sine of the angle between them. The other thing that you derived in your homework is something called the law of sines, right? Which is a really useful fact about triangles. It says that sine of capital A over little a is equal to sine of capital B over little b is equal to sine of capital C over little c. What this basically says is that if you have any triangle, it doesn't have to be a right triangle, any triangle at all, if you take the sine of some angle and divide by the length of its opposite side, that ratio will be the same no matter what angle side pair you choose. So sine A over little a, sine B over little b, sine C over little c, they're all the same. And you can use this information to solve triangles, as you kind of saw in the homework. Just one quick note, sometimes the law of sines is written this way. Sometimes it's written with the lengths on top of the fractions. So little a over sine A, little b over sine b, little c over sine c. It doesn't matter. In fact, you can switch between the two forms. They're equivalent. Whatever one is more convenient. Okay, so what we're going to do today is we're going to, so in your homework, you learned how to use the law of sines to solve triangles given two angles and a side. So I had you solve at least one triangle where you knew two angles and you knew one side, and you'd use the law of sines to find the others. So something like this, if I gave you a triangle and I was like, oh, this is 32 degrees and this is 17 degrees, and the length of this side here is whatever, 12. Find the remaining angles and find the remaining sides of the triangle. That's what you saw how to do on your homework. It's pretty easy, as you saw. You just use the law of sines to find a missing side. So for example, you could say whatever this side is here, let's just call it little b. It doesn't matter what you call it, but I could say that b over the sine of its opposite angle, so that would be 17 degrees, is going to be equal to 12 over the sine of its opposite angle. Here you can see I'm using this version of the law of sines. and then you just solve for b, right? And obviously, since these three angles add up to 180, you can find this missing angle, and then another application of the law of sines will give you this side right here. Okay, that's what we did for homework. Let's talk about new stuff. So what are we doing today? Well, as I said last time, in your homework, you solved triangles given two angles and a side. So in other words, last time what you saw was how to solve triangles involving two angles and a side. You could call that AAS, or you could call it ASA, or you could call it SAA. They're all the same thing, and you use the law of sines. Today we're going to learn how to solve triangles involving a different collection of information. Basically, we're going to learn how to solve SSA triangles. Notice the difference, that there are two sides and an angle. And I also want you to notice that the A is not in between the two S's. That's important. This is a really interesting case. This is sometimes called the ambiguous case. Ambiguous case. And I'll explain why in a moment. Let me just point out one thing. SSA literally spells ass backwards, and I think that's a good thing to keep in mind, because this case, the SSA case, is kind of the weird case. As it turns out, there are three different possibilities. In fact, it's possible that given SSA information, there are no solutions at all. It's the strangest of all the triangle cases, and knowing that it literally spells ass backwards is a good way of remembering it. It's the ass backwards case. So I just want to be clear about what this means. Like, what does it mean to be given SSA data? What it means is that you're given two sides and an angle. And furthermore, the angle you're given is not the angle in between the two sides you're given. Okay? That would be SAS, which is a different phenomenon. So as we're going to see, there are really three possibilities. Okay? Given SSA data, there's three things that could happen. There could be one triangle, there could be two triangles, or there could be no triangles. And what do I mean by that? What I mean is, given SSA data, it's possible that one and only one triangle corresponds to that given data. It's also possible that actually two genuinely different triangles match the given data. And finally, it's possible that actually there are no triangles which match the given data. And what I'm going to do is an example of each one and show you how that works out. So let's suppose that angle A is 43 degrees, little a, that's the side length, is 81, little b is 62. The way that you should always handle these things is start by drawing a picture. Okay? I won't give you a picture, I'll just give you angle and side information. So you should start by putting it into a picture. Remember the convention, little a is always opposite of big A, and so on, right? That's important that we follow that. So if angle A here is 43 degrees, then little a is 81, so this has to be 81, and little b is 62. All right, so now we've got a picture, and obviously what we need to do is find the remaining portions of the triangle, like find these two angles and find that missing side. One thing that you might notice is that you can do the law of sines, right? And you'll have only one unknown. So if I say, for example, 81, that's side A, over the sine of its opposite angle, that's 43, so this guy over the sine of this guy, that's going to be equal to this guy, 62, over the sine of its opposite angle. That's angle B, right? Notice that in this equation, there is only one unknown, B. If you ever write down the law of sines and you have two unknowns, then you need to use the law of sines differently. Okay, there's actually other things that I could have written here, like just quick detour. I could have also written down 81 over sine 43 is equal to little c, that's the length, over the sine of capital C. This equation's true. Like whatever little c and big C are, this equation will be true. but it's useless because it has two unknowns, little c and big C. So that would not be helpful. All right, you always want to set up your equation so that there's only one unknown. Anyway, this is like the equations you did on homework, except the angle is the unknown now, not the side. So if we solve for sine of b by cross multiplying or whatever, I guess you could say this is like 81 sine capital B is equal to 62 sine of 43 cross multiplying. This will give you, let's see, so I'm going to make sure I'm in degrees. So sine of 43 is that, and then I'm multiplying by 62, right? And then to get the sine b by itself, obviously I need to divide both sides by 81. So divide that by 81. I find that sine of b is 0.522. Cool. Great. Well, guess what, guys? That's a trig equation, right? I mean, we just did a whole unit on how to solve these kinds of things, right? And what should you notice? You should notice, oh, 0.522, that's not a unit circle angle, right? And so you have to use your calculator. So you use your calculator, and you take the inverse sine of 0.522, and we get 31.4, let's round to the next decimal place, 31.47 degrees. Cool, so B is 31.47 degrees. That's great. The thing is, though, you know that there are other solutions to this trig equation, right? Technically, what are all the solutions to this equation? Well, this is one base solution, right? Any angle coterminal with this guy would also be a solution, so maybe I should write plus 360n. But there's also a second base solution, isn't there? Like there's a whole different angle on the unit circle whose sine is 0.522. Do you remember how to find it for sine? You have to subtract it from, well, in radians it's subtracting it from pi. In degrees that would be subtracting it from 180. So the second base solution will be, if I take 180 minus my first base solution, 31.47, I get 148.53. 148.53. And then technically any angle coterminal with this guy would also be a solution. So these two formulas gives you, these two formulas give you the infinite number of solutions to this equation. However, remember that B is an angle inside of a triangle, right? Which means that it needs to be less than 180. So even though I didn't write it, we technically have a restriction here. Bigger than 0, it would make sense. It wouldn't make sense to have an angle of 0 degrees inside of a triangle. And also it should be less than 180, right? So even though I didn't give you this restriction, it's implied by the fact that angle B is an angle sitting inside of a triangle. With that in mind, we can see that these two formulas only give you one solution each, right? If you add even one copy of 360 to either of these guys, you immediately go over the cap, okay? And so really the plus 360n is not going to give you any additional solutions in this problem. In fact, it never will. Throughout this unit where we're solving triangles and you do the inverse sine function and so on, you don't have to worry about the plus 360n for this reason right here, okay? But I just wanted to be clear about that. Now, even forgetting about the plus 360n, we actually still have two different base solutions. What's up with that? This is really what explains the fact that it's possible to have one triangle or two triangles. The thing is, this first base solution here will always be like a solution. It'll always be a viable, possible value for B. The second solution may or may not. And whether it is or not depends upon whether it's too big compared to the angle that you already know. We already know that capital A is 43 degrees. Can this angle be 148.53? The answer is no. And the reason why is this angle plus the known angle that you already have goes over 180. 148.53 plus the known angle A, 43 degrees, gives you 191. That's too big. That's too big, right? The sum of the angles has to be 180. So the sum of this and this can't possibly be bigger than 180. So this angle in this case, in this particular problem, is not admissible. It's just too big, okay? And we only have one possible value for B. So this angle right here is 31.47 degrees, okay? And what I'll say is that once you know this angle, the rest of the problem is pretty straightforward. Obviously, you can figure out angle C because of the fact that these three angles add up to 180. And then once you know angle C, another application of the law of sines will give you little c, right? You could just say this guy or the sine of this guy is equal to, say, 81 over the sine of 43, all right? Now, because in this particular problem, the second base solution was not admissible, we have one and only one triangle which matches the initial given data. The triangle is given by, angle B is 31.47. Angle C is whatever is determined by the fact that these three guys have to add up to 180. And this side will be determined by the law of sines again. But in other problems, this second base solution will actually be admissible. It'll actually be not too big. When that happens, when the second base solution is not too big, that is, the second base solution plus the known angle isn't over 180, when that happens, you actually have two genuinely different triangles, okay? You have two different values for B, and of course those two different values for B lead to two different values for C, angle C, that is, and that leads to two different values for little c, which means you actually have two totally different triangles which match the initial given data. That's what I say when I mean you can have two different triangles. Okay? So in summary, with SSA data, you're always going to use the law of sines, and you're going to have to solve this trig equation. Your unknown will be an angle. You'll get two base solutions, right? One with your calculator, the other by subtracting the first from 180. And whether you have one base solution whether you have one triangle or two triangles, just depends upon whether the second base solution is actually acceptable or not. The first one always will be, guaranteed. Like the one you get from your calculator, that'll be acceptable. The second one will be bigger, and you just have to ask, is it too big, right? If it's too big, then you only have one triangle. If it's not too big, then you actually have two different triangles, and you have to solve both triangles, okay? Now, there is one more possibility. It's possible that there are no triangles which match the given data, okay? Let's do an example where that happens. Let's suppose that, and this won't take long, let's suppose that angle A is 75 degrees, and little a is 51, and little b is 71. Okay? So as I said before, whenever you're given this textual information, you should always draw the triangle. Makes it way easier to understand what's happening. So here's my triangle. Let's call this capital A, capital B, capital C. It doesn't matter what you label things, as long as you follow the convention that little b is opposite of angle B and little c is opposite of, right, and so on. So this is 75 degrees. Little b is 71. Little a is 51. Okay? And here's my triangle. Once again, you'll notice that you can use the law of sines in such a way that you only have one unknown. Namely, I can write the sine of 75 over its opposite side, that's 51, is going to be equal to the sine of capital B over its opposite side, 71. Right? You can solve this equation for sine of B, cross-multiplying, however you want to think of it. I'll skip to the chase. Really, all you have to do in this equation is multiply both sides by 71. When you solve for sine B, you obtain the following. You get 1.3447 is equal to sine of B, right? That's a trig equation. And, if you remember, in the unit we just finished, if you have an equation like this, sine of b equals this number is bigger than 1, which means there are no solutions, right? The sine of an angle can never be larger than 1, nor can it be smaller than -1, right? The sine function only takes values between negative and positive 1. So this equation has no solutions, which means that there are no values of b that could possibly satisfy this equation, which means that there's no triangle that could possibly match this initial data. That's what I'm talking about in the third possibility when I say it's possible to have no triangles. Okay? So in summary, if you're given SSA data, that's side-side angle, that's where you have two sides, and the angle you're given is not in between the two sides, right? Notice that here the angle is not in between the two. That's what's meant. That's why we don't put the A in between the two S's. If you're given SSA data, that's ass backwards. That's the weird case where there are three possibilities. The data you're given could correspond to just one triangle, or it could actually correspond to two triangles, or it could correspond to no triangles. Okay, and you'll use the law of sines to get a trig equation like this, and what comes from that kind of dictates whether you have one, two, or none. Right? You'll get, if there are no solutions, then obviously there are no triangles. If there are solutions, you'll have two base solutions, right? Like we did in the previous problem. If both of them are admissible, right, then you have two genuinely different triangles, and if only one of them is admissible, then you have just one triangle.